In this lecture, let's explore about the RTOS tick interrupts and the RTOS tick frequency. So this is our pre-RTOS customization article from preRTOS.org, where they have mentioned how to prepare your pre-RTOS config.h file. So you have to include all these macros, isn't it? So in this lecture, let's explore more about the RTOS ticking. So first, let's explore about the macro config tick rate hertz. Okay, so this macro says that this is the frequency of the RTOS tick interrupt. So the documentation says that this is the frequency of the RTOS tick interrupt. So what we can make out of this sentence, that means the RTOS uses a timer peripheral which is used to generate the interrupt that we call as kernel tick interrupts, and this macro defines its frequency. That's it. So if the frequency is 1000 Hertz, then the RTOS tick interrupt will be generated for every 1 milliseconds. And if the tick rate hertz is equal to 250, then this kernel tick interrupt will happen with the resolution of 4 milliseconds, isn't it? So now the question is, why does the RTOS need these tick interrupts? Okay, so let's explore that in the next slide. So the simple answer is to keep track of time elapsed. That means, is there any global variable called tick count, and will it be incremented by 1 whenever each time interrupt occurs? So yes, exactly. So there is a pre-RTOS global variable called tick count, and it will be incremented whenever the tick interrupt occurs. Okay. And again, so why all these things are needed? Let's understand that in the next slide. Let's say a pre-RTOS task wants to sleep for 100 milliseconds. You will explore more about sleeping or blocking APIs later in the course. But for a time being, let's say a task wants to sleep for, say, 100 milliseconds. Okay, so it calls this RTOS API. So now it's a duty of the pre-RTOS kernel to wake up this task after 100 milliseconds, isn't it? So how do you think the pre-RTOS tracks the completion of 100 milliseconds? So the answer is, the pre-RTOS calculates the time with reference to the tick count variable. So you know that tick count variable increments for every kernel tick interrupt, isn't it? So if the tick rate hertz value is 1000, then your tick interrupt happens for every 1 milliseconds, isn't it? So that means the resolution of the tick interrupt is 1 milliseconds. So if tick count variable is incremented by 100, that means 100 milliseconds have been elapsed, isn't it? So this task will be woken up by checking the value of tick count variable at each kernel tick interrupt. If the tick count value is incremented by 100, then task will be woken up. So that's how the pre-RTOS track the time elapsed in the system. And for that, tick interrupts are very essential, and the tick interrupts are usually generated by any timer peripheral. Now, the tick interrupt is also used for scheduling, or you can say context switching. Yes, the RTOS tick interrupt is also used for the context switching to the next potential task. Okay, so this is also one of the major use of the RTOS tick interrupt. The RTOS tick interrupt is very essential to implement the multitaskable environment where context switching is one of the important tasks which must be implemented. Okay, so what is context switching? Context switching means removing a running task and replacing that task with a next potential task. Okay, so that we call a context switching. So whenever the RTOS tick interrupt happen, the tick ISR runs. Okay. So in the tick ISR, all the ready state tasks are scanned, okay, to check who has got the highest priority, and determines which is the next potential task to run on the CPU. If any potential task is found, the RTOS tick ISR will then trigger the context switching handler. Okay, so it won't do any context switching. So it just triggers another exception, okay, or another handler, okay, which will take care of context switching. That means saving the context of the old task and switching in the context of the new task found. The context switching handler then takes care of switching out of old task and switching in of new task. Okay, this is what we call context switching. And remember that the tick ISR doesn't implement any context switching code. Okay, so it only triggers the context switching code that we will explore later when we are exploring about context switching handlers. Okay, all right, so now let's move forward. So does kernel use any timer peripheral to issue tick interrupts? Yes, of course, because it should be implemented using timer hardware of the MCU. So almost all MCUs, they have got the timer peripherals, isn't it? So one of the timer you can dedicate, okay, to generate the RTOS tick interrupts. Okay. So now in the market, there are a lot of microcontrollers which are based on ARM Cortex-M architecture. For example, the Arduino Duo board which we are using in this course is based on Atmel SAM-based devices. So Atmel's SAM-based microcontrollers are actually based on ARM Cortex-M3 architecture. And STM has a lot of microcontrollers, okay, which are based on ARM Cortex M0, M3, M4, etc. And most of the LPC microcontrollers are also based on ARM Cortex M. If you are using ARM Cortex M based microcontrollers, then ARM Cortex processor itself has got one timer called SysTick timer. This is just like your other timer peripherals. Okay, there is nothing special about it, but it is provided by the processor itself. That means it is provided by the ARM itself, okay, rather than it is implemented by the microcontroller vendor. Okay, so if you are using ARM Cortex based MCUs, okay, then you can use this timer peripheral to generate the kernel tick interrupts. Okay, so all the pre-RTOS official port for Cortex processors actually use SysTick as the kernel tick timer or OS tick timer to generate the tick interrupts. All right, and if you have a microcontroller which is not based on ARM Cortex family of processors, okay, then you can use one of the timer peripherals for this purpose, no problem. Okay, but in the case of microcontrollers which are based on ARM Cortex M family, they typically use the SysTick timer. Okay, great. So in the next lecture, let's explore what exactly the pre-RTOS tick ISR does. Okay, so we already know that the OS ticking is implemented by the SysTick timer. Okay, so whenever the SysTick timer interrupts the processor, the tick ISR or the SysTick timer ISR will run. So in the next lecture, let's explore what exactly is implemented in the SysTick ISR implementation. Okay, so I will see you in the next lecture.